Okay, so our next speaker will be Dickstein from Tel-Aviv University. He will speak about relative symplectic cohomology of pairs.
Okay, thank you very much for the invitation. So, as you said, my name is Adi Dickstein from Tel-Aviv, and today I'm going to talk about relative symplectic cohomology of pairs. This talk is based on a joint work with Yaniv Ganor, Leonid, Polterovich, and Frol Zapolsky. So, I'll start with some review on singular cohomology, and then I will explain the analog in the case of relative symplectic cohomology, and the way I will pack this tool will be ideal valued quasi measures. So this will be a measure-like object that allows us to prove a result in symplectic rigidity. So let me start. Singular cohomology. So what is a singular cohomology? Is a functor from topological spaces to Abelian groups. And it has a standard model of chain level, which is also a functor from topological spaces to chain complexes. And from reality, we know that if we have a subset A of X and a smaller subset B, then the restriction map from X to B equals to the composition of the restriction from X to A and then to B. And what is the cohomology of pairs? The cohomology of the pairs of a pair is defined to be its complex is that we define to be the kernel of the restriction map from X to our subset, and then we just have to take homology of this complex. So this is the notion. This is the relative symplectic the symplectic cohomology of a pair. Now, singular cohomology satisfies Meyer-Pietruis in case of excisive couples. Excisive couple is excisive if it satisfies some algebraic condition related to the chain complex. And also we have cup product on singular cohomology. So this is a product on the cohomology of the pair a x comma a, and we can also define a map from the cohomology of x comma a times x comma b for two sets A and B. But in the general case, the target will be the cohomology of x comma the intersection. If we want to upgrade it to the case of x comma the union, we have to assume that our couple is excised. Now, what happens in the case of the cohomology of the relative symplectic cohomology? So in relative symplectic cohomology, what is it first? So we have a closed symplectic manifold, and Varolgunes defined a functor called relative symplectic cohomology from compact subsets of the manifold to lambda algebras. Here lambda is the universal Novikov field, and the product structure was defined by Tonkonov and Varolgunes. And in the simplest cases, the relative symplectic cohomology of the manifold is just quantum cohomology as an algebra, and also the relative symplectic cohomology of the empty set is 0. So also we have Varolgunes defined a model of a chain complexes. So what is the definition or a sketch of the definition? Given a compact subset, we can consider a sequence of non-degenerate Hamiltonians, which is monotone and converges to 0 on the set and to infinity outside of the set. Then we define the complex of K to be the direct sum, the direct limit of the Floer complexes with a completion. The purpose of this completion is to kill, in some sense, as in some ideal situations, the orbits that are not included in a neighborhood of K. So this complex is well defined just up to homotopy equivalence. So the cohomology itself is well defined. And also we have restriction maps using that we can obtain by continuation maps, and they are also defined up to homotopy. For our purpose, we define the notion of relative symplectic cohomology of pairs M, K, or K the subset. And for that, we have to use kind of homotopy kernel. So we used a model of a homotopy kernel, which is co-cone. What is a co-cone of a map F from C to C comma? As a model is just the sum of C with C prime with a shift of the indexes, and F itself appears in the formula of the differential. Then we could define the complex of M, K to be the co-cone of the restriction map in the chain level from the complex of M to the complex of K. This object is also defined up to homotopy, and we defined its homology to be the homology of M, K, the relative symplectic homology of M. Now we can ask about Meyer vietories, and what Varolgunes proved that we have Meyer vietories if and only if our set satisfy some algebraic condition called descent. It is parallel to, in some sense, to the case of to the definition of excisive couples, but a bit different. And the question is, can we describe such sets in some geometric language? So a definition for commute sets. So we said that two sets commute if there are Poisson commuting functions such that our sets are exactly the zero sets of the function. For example, if we have two disks on the sphere with empty intersection of the boundary, then these sets commute. And on the other end, in dimension 2, if we have non-trivial intersection of the boundaries, then the sets do not commute. Here, the intersection in this case is a transversal, and that's why what implies in dimension 2 that the set do not commute. And Varolgunes proved that in the case of commuting set, we get that our sets are in descent. So if we have two commute sets, then we get Meyer vietories for the relative symplectic cohomology. Now, what we proved, we construct a product structure on a relative symplectic cohomology of pairs, and like the same in the case of the singular cohomology, we have a product for two subsets K and K prime from the relative symplectic cohomology of M, K times M, K prime to M, the intersection. And what we proved that if K and K prime are in descent, then we can upgrade this product and stuff that the target will be the relative symplectic cohomology of M, the union. And also we prove that this product commutes with the restriction maps. Now, how we can take a few of this information in a geometric tool. So we defined a new object called ideal valued quasi-measure. This is a symplectic analog of ideal valued measure that was defined by Gromov. And the definition goes like follows. So let M be a closed symplectic manifold and A be a graded unital algebra. So what is an ideal valued quasi-measure? Is an assignment from open sets of M to graded ideals of A, and it satisfies several axioms, for instance, normalization, monotonicity, additivity for disjoint union of finite disjoint unions, simp zero invariance, and also vanishing for displaceable sets. And two extra axioms are quasi-multiplicativity. It says that if U and U prime commute, then the product of their measures is a subset of the measure of the intersection. And also, last axiom is the intersection axioms. And it says that if we have a cover of M by two sets, then the measure of the intersection equals to the intersection of the measures. And also we can extend this object to compact sets just by taking intersections on an open set that are contain a specific compact set. Let me give you an example. So on the sphere with normalized area, you can take any algebra, and I will define, we define an ideal valued quasi-measure on connected open set, U, for instance, U, as follows. So for in the case that U is contained in a small disk of small open disks, small here is of area at most half, then the value will be 0, and in any other case the value will be A. So if U is a small disk, then its measure is 0, and on the other hand, if U is a thin annulus that is contained contains the equator, then its measure is the algebra itself. And on the right side, you can see two annuli, very thin with small intersection. Then the measure of these two annuli are the algebra itself, but the measure of the intersection is just 0. So you can see that we don't have the inclusion that the quasi multiplicativity axioms told us, but in this case the sets do not commute, so this is not a problem. Great. Now, how goes our construction? So we used relative symplectic cohomology, and what we did, for an open set, we defined tau of U to be the kernel of the restriction map from the relative symplectic cohomology of the manifold to the relative symplectic cohomology of the complement. And we called this object the quantum cohomology IVQM of our manifold. And what we proved is that this object is actually a really IVQM on the with respect to the quantum cohomology of the manifold. And here I'm a bit cheating you, since we have to use a kind of a regularization process to get a continuity with respect to increasing unions. So we had to use some unions and intersection of this object, but this is the heart of the construction. So you can think about this formula, and this is, for this talk, is very, very good to remember it. Okay, and why we had to develop all the theory of a relative symplectic cohomology of pairs is for proving the quasi-multiplicativity. So this is the main from our viewpoint, this is the main property of a ideal value quasi measures. So, and the proof of it involves relative symplectic cohomology of pairs. And example of our construction is just the last construction where we take A to be the quantum cohomology of the manifold. Some computational results. So on the torus, standard torus, with coordinates P and Q, given given K, which is an integer between 1 and n, we can consider the coisotropic torus T, which is the set of all the points with K first coordinates, which are 0. And by a calculation, we showed that the IVQM, the quantum cohomology IVQM of this T is the ideal, which is generated by the differential of the K first coordinate of the wedge of the K first coordinates. Additionally, we proved kind of a unit formula, and using it, we proved that the measure of the product of T with an equator of the on the sphere contains the tensor product of the measure of T with the tensor product with the measure of L, which is just the quantum cohomology of the sphere. Okay. And applications to symplectic rigidity. So first, a very important application is non-displaceability of two sets. So given two sets, compact two sets, if we prove that if the product of their measure is not 0, then we can't displace K from K prime by simp0 elements. So for instance, on the right, from topological reasons, we can displace these two circles, but also the product of their measures is not 0. And on the left, we can displace the circles by simp0 elements, but not using ham elements. So in this case, we can't say nothing about ham non-displaceability, just about simp0 non-displaceability. And the proof is very easy. So if we can displace K from K prime using an element P, then phi K and K prime commutes. Using the quasi-multiplicativity, we get that the product of their measures is 0. And also we used here the normalization, since the measure of the empty set is 0. And on the other hand, using the invariance, we know that the measure of a phi K is just the measure of K. Thus, we get a contradiction. So, a non-trivial example using that we got using this observation is the following. So, on the product of this the two n-dimensional torus and S2, we can consider two Lagrangians. One is is T n times the point, and times also an equator in the sphere. And the second one is the orthogonal Lagrangian in the torus times another equator. And by a direct calculation from our observations, we get that we can't displace K from K prime by simp zero elements. And the proof is just calculation. Also, just to say that that with smooth or more than that, volume preserving isotopies, we can displace K from K prime, and the case of Ham non-displaceability was proven by Kawasaki. Okay, another result of symplectic rigidity uses the notion of involutive maps. So what is an involutive map on a symplectic manifold? Is a map to a smooth manifold, for instance, so that the pre-image of any two continuous smooth functions on the target, the pullback gives us Poisson commuting functions. And examples for involutive maps could be maps to Rn with Poisson commuting coordinates, or projection from a T to N to Tn, which is just a Lagrangian fibration. So we get here also involutive map and involutive. And as an application, or here I'll just show you an abstract formulation, and then I'll show you a specific example. So given a closed symplectic manifold and an AIVQM for a specific algebra, and also an involutive map to a manifold of dimension D, we proved using a symplectic analog of a result of a Roman Carousel, that if we have an ideal in the algebra so that its D plus first power is not zero, then there is a fiber of our involutive map that intersects all the compact subsets with the property that I is contained in their measure. So we have several sets that I is contained in their measure, and we know that there is a fiber that intersects all of these sets. And let me show you a specific example of this. So on the 6 torus with coordinate P1, Pi and Qi, we can consider 3 families of 4-dimensional coisotropic subtori as follows. So we put A, B, and C from we consider A, B, and C from T2, and we define T1 of A to be the subtori that is defined to be the set of all the points with K1, K2 equals A. T2 will be the set of all the points with P1, P3 equals B, and C will be T3C of C will be the sets of all the points with P2, Q3 equals C. Then we consider the union T of ABC to be the union of T1 of A, T2 of B, and T3 of C. And what we proved, that given an involutive map on the 6 torus times S2 to any surface, 2-dimensional surface, so any of such a map has a fiber that intersects all the subsets of the following form: T of ABC times any quadratic. And all the assumptions here are essential for the involutivity is essential, the dimension of the target is essential, and also if we omit one of these families, then the following also is not true. Okay, and how the proof goes.
Excuse me, I did to interrupt. So I'm not sure exactly, but I think you're running over time, so you consider concluding reasonably quickly.
Okay, thank you very much. So if so, I think this is a good point to stop. So thank you very
sorry.
much. And no problem. Thank you very much.
Thank you very much.
Thank you. So, and any question if you have?
Are there any questions?
Yeah, I had a question.
Yes, sure.
Is there in that the non-displaceability, do you have some special cases where a converse might be true? So like a two-dimensional symplectic manifold and some class of Lagrangians where it's displaceable if and only if that product vanishes?
In a surface, are you asking for two Lagrangian that are non-displaceable one from the other, even only if the product is not zero? In some cases it can be true, but in general, if our Lagrangian is not heavy, then the measure will be zero. So it's really depend on our situation. There are sometimes topological reasons, like in the case of the torus, and there are no polymorphic spheres. So that's one of the reasons why we just saw the topological restrictions there in the torus.
Okay, thanks.
Thank you.
Any other question? Okay. If not, let's thank you again.
Thank you.